Hi, Integrated Math 1 students. Mrs. Robinson here to work Practice Benchmark Chapter 5 with you. This chapter is on exponential and radical functions. So instead of doing arithmetic sequences where we had equations of lines, we're going to do geometric sequences where we have exponential functions. They go up really fast. I always say, I wish my bank account would increase exponentially, but that never happens. So let's start with the first one. Zero exponent. Anything to the zero power is 1. It doesn't matter what it is. 5 million to the zero power is 1. There we go. To the zero power is 1. Let's see. 2 to the zero power is 1. Negative 1/5 to the zero power is 1. Anything to the zero power is 1. So if I take this to the zero power, I do get 1. Careful. Remember order of operations. Please excuse my dear Aunt Sally. Okay. I do exponents, I do parentheses, then my exponents. Then I multiply and divide and add, subtract. So I did my parentheses and my exponent and I got 1. This negative is on the outside, is not raised to the zero power. It's on the outside. So I actually have negative 1 because after I do my exponent, then I'm multiplying by a negative 1. Okay. Careful. That would be different than if I had negative 15 p to the zero power. This would give me 1 because it's all inside the parentheses raised to the zero power. That is a negative 1. All right, on to the next one. Also, this negative is on the outside of the parentheses. This is 5 to the negative 2 power. Remember, anything to the negative 1 power, if I want to get rid of that negative exponent, I bring it to the denominator. This would be 1 over x. X to the negative 2 power would be 1 over x squared. So 5 to the negative 2 power is actually 1 over 5 squared. However, I do have to multiply that by negative 1 on the outside. So this is going to be negative 1 over 5 squared. Now 5 squared is 25, so this would be negative 1 over 25. Careful with those negatives, all right? Let's go on to the next. All right, number 3. Number 3 is got some negative exponents in it. This is all multiplied together. So I can go ahead and divide things out because it's all multiplied. This says h to the 0. That's really weird while that's smushed. But anytime you have anything to the 0 power, it's just 1. So let's start there and go, all right, well, that's 1. Anytime I have a negative exponent, remember, x to the negative 1 is equal to 1 over x. Okay, so if I have g to the negative 5th, it's equal to 1 over g to the 5th. So I can take this, because this is all multiplied, and just move it to the denominator and make it g to the 5th. Now the same for this denominator. I can go ahead and take this and move it to the numerator because it's h to the negative 2. To make it a positive exponent, I take it up and make it h squared. You're not simplified unless you have no negative exponents. You have to have all positive exponents to be simplified. Now, why do I get to bring this up? Think about this concept. H to the negative 2 is equal to 1 over h squared. I have it on the denominator. So if I had 1 over h to the negative 2, I just bring it up and make it h squared because technically this would equal to 1 over, this is 1 over h squared. So you have a fraction divided by a fraction, or you can make that a fraction. So you would have this, the keep, flip, change scenario. Keep the numerator, or keep the top, flip the denominator, h squared over 1. Change this divide to multiply. And you'd have 1 times h squared over 1, which is h squared. So hence, if you have 1 over the negative exponent, bring it to the numerator and make it a positive exponent. So h to the negative 2 power is 1 over h squared, and 1 over h to the negative 2 power is just h squared. So to make this positive exponent, bring it to the numerator. That's all you have to do. Negative exponents on the numerator, bring to the denominator. Negative exponents on the denominator, bring to the numerator. And what I'm left with is 10. I have an f here. F was just to the first power. I'm just going to leave my f. Okay. G I brought down. And the h to the 0 turned to 1. So I have 10f, and then I have h squared here. H squared over the h squared went up, and what I'm left with on the denominator is g to the 5th. And that is most simplified. There's no negative exponents. Nothing else divides out, and you're done. Okay, we're going to evaluate this one, y equals 4. Careful about negatives. Once again, You've got a negative y inside the parentheses. We're taking that to the negative 3 power. Well, anytime you have something to the negative exponent, I'm going to take it to the positive exponent by taking its reciprocal. This is 1 over negative y to the 3rd power. Okay. Now I'm going to plug in the 4 for y. This is 1 over negative 4 to the 3rd power. Okay, and that is in the parentheses. So what does that mean? That means negative 4 times negative 4 times negative 4. Well, negative 4 times negative 4 is positive 16. Positive 16 times negative 4 is going to be negative 64. So this will be 1 over negative 64, or negative 1 over 64. All right, let's evaluate this function. 2 times 3 to the x for when x is 5. Just plug in 5 for x. 2 times 3 to the x. Remember your order of operations. Please excuse my dear Aunt Sally. Okay, you don't do multiply first. You always do what's in parentheses, then you do your exponents. Then you do your multiplying. So we're going to go, this is going to be 2 times 3 to the, and I wrote x again, and I meant to write a 5 there. 2 times 3 to the 5th. Well, I'm going to do 3 to the 5th first. So 3 to the 5th power is 243. Then I'm going to multiply that by 2. And I just did it on a calculator, and I'm going to get 486. There you have it. Okay, I want to write this expression as a decimal. Remember what the negative exponent means. You can also think of it as this is in scientific notation. So I'm going to take 6, and my decimal is here after the 6, and the negative moves me into the left side notation. It's going to make this smaller. So I'm going to move 1, 2, 3 spaces over. And I'm going to have 0.006. Okay, another way you could think of this is 6 times, since it's to the negative 3rd, 1 over 10 to the 3rd. Okay. Or 6 times 1 over 10 to the 3rd is 1 and 3 zeros. And this would be 6 divided by 1,000, which is going to give you 0.006. But just know your scientific notation. Because it's in scientific notation, you can make the number smaller by going to the left. If that was a positive exponent, you would move to the right. Okay, this problem looks monster scary, but it really is quite a simple problem. Just read through it. The city library will be increasing the number of books it has to loan at a rate of 5% per year. Okay, so they're getting more books. Yay! It currently has 40,000 books. The number of books they will have in any given year is modeled by this function. It's exponential because it's increasing 5% per year, where t is the number of years. How many books will the library have in 8 years? Well, they give you the function. This is why this is much simpler than it looks. H of t is, you start out with the 40,000 books you have, and you're going to multiply that by 1.05 times the number of years to the t. T is the number of years. So I'm going to start with the number I have. That's why you go 40,000 times 1. And then you're going to multiply it by 5% more. So it's going to add 5% more, and you're going to do that the number of times you have here, t times. Okay. So this is an exponential equation or function. So we want to know in 8 years. So we're going to do this 8 times. We put an 8 here because it adds 5% 8 times. So we go h of 8 for a time is 40,000 times 1.05 to the 8th power. Now I just do this on a calculator. So I'm going to get out a calculator and do 1.05 to the 8th power. Now if you have a, just so you know, if you have a phone calculator, let's see, on a phone, if you turn it to the side, you get a lot more options. And oftentimes they have an X to the Y button, okay? So you could type in 1.05, and then you do X to the Y, and then take that to the 8th power. And that would give you your amount that you're going to multiply. Or if you have one of these, I would just go 1.05 and take it to the 8th power. And I would get 1.477. And it's the same on my phone calculator, okay? So if I take this to the 8th power, I'm going to get about 1.4774. You can write that down. I like to just keep this value in my calculator and then just multiply that by 40,000. It keeps it most accurate. And I'm going to get approximately, okay, after 8 years, I'm going to have 59,098 books. So approximately 59,000 books. And you could round that to 2 decimal places. You're not going to have 0.22 of a book. You're just going to have 59,098 books. I would round down because you're not going to have a part of a book. That doesn't make any sense. Okay. Okay, graph the exponential function. Remember, exponential functions, when I say something increases exponentially, you're going to think it's going to go up really fast. So your exponential function should look like a curve that goes up really fast, okay? Unless it's flipped and whatnot. But let's go ahead and when you're graphing an exponential function, know that it should look like that. Something that always happens, make an XY graph. Start with 0. Anytime you bring an exponential function to the 0 power, anything to the 0 power is equal to 1. Okay, so you should always have that 0.01. Unless you're like adding 5 and you're shifting up or something, then you would have 0.5. But you should, when you plug in for the basic function, you plug in 0, you should get out 1. If you have an a value here, if I plug in 0, I would get out the a value, meaning if I had something like y equals to, I don't know, 10 times 5 to the x. If I plug in 0 here, I'm going to get out 10. Okay. So just be aware. But your basic function, you should always have plug in 0. Anything to the 0 power is 1. All right. Now let's plug in 1. 5 to the first power is 5. Plug in 2. 5 squared is 25. You can see this is going to go up really fast. It's already off my graph. Let's go to the negatives. When you plug in negatives, you don't get out negative values. You get out fractions. 5 to the negative first power, 5 to the negative first power is equal to 1 over 5. You get 1/5. Okay. 5 to the negative 2 power, 5 to the negative 2 power, you get out 1 over 5 squared, which is 1 over 25. So my numbers are getting itty, itty, bitty. So what happens is I go in this negative direction. Instead of having bigger numbers, I get smaller and smaller and smaller. Let's graph it. Plug in 0, 1. So there's my point. 0, 1 I'd have for any basic exponential graph. Plug in 1, 5. You go over 1, up 1, 2, 3, 4, 5. Now I'm going to plug in 2, 20. I'm going to go over 2, and I'm going to be way up here. So it goes up really fast. Now do negative 1. I go negative 1, and I'm only going up 1/5. It's just not even halfway. Plug in negative 2, I go up 1/25. Negative 2, I go up here. Negative 3 is going to be even smaller, so it's going to start to hug this line. It's not going to touch it, but it's going to hug it, and then it's going to go up really quickly like this. Okay, so that is what y equals 5 to the x should look like. Okay, this guy I want to solve for x, and I've got an exponential here. Now, usually when I solve for x, if I have exponentials, I usually use logarithms to undo them, right? I'm going to divide both sides. I'm not going to use logarithms here. I'm going to divide both sides by 10 to get this by itself. And I'm going to get 3 to the x equals 90 divided by 10 is going to be 9. Now, I can't root this because I don't know what this is. And we're not using logarithms here. Let's just use logic. 3 to the what power gives me 9? Well, if I square 3, I'm going to get 9. So that means that x had to be 2. You could think of it like this. If this is a base of 3, can I get this to be a base of 3? Here's another way to think about it. Can I get 9 to be a base of 3? I can. 9 is 3 squared. So if 3 to the x equals 3 squared, x has to be 2. And that's how you solve those. So first, get this by itself, then work those and see if you can get them to be the same base, then you'll know what x is. It's a logic. Okay, determine if this situation can be modeled by linear or an exponential function. How do you know? It can be modeled by a linear function if there's a common difference. Okay, meaning I'm going to add a certain number or subtract a certain number. It can be modeled by an exponential if there's a common ratio. Okay. I'm going to multiply the first number by another number, another number, another number. That's a common ratio. Okay, that's your exponential. Linear would just be your basic y equals to mx plus b. Okay. And then where your slope here would end up being your common difference. Your exponential or your common ratio would look like this. Y equals some term, okay, times your base to a power. And that base being your common ratio, right? So if we look at this, am I adding a common difference or multiplying by a common ratio? The value of Adrian's baseball card collection has increased by 2% per year. If I said Adrian's baseball collection had increased by 2 cards, then I would add 2 cards each year. But no, 2% per year. So I'm going to multiply the previous year by 2% and multiply the previous year by 2% and keep adding to the next one and to the next one. So this would be a common ratio if it's increasing by a percentage. Okay, so this would be exponential and it would be a common ratio because it increases by 2%. Real quick, if you look back at this one, okay, this one increased by 5% per year. So you start out with your A value, which was 40. That's our initial value. And then you multiply it by 1.05. Here we would multiply it by 1.02 because it's a 2% times the number of years. And that would be a function for that. It didn't ask you for that function, but it might look something like this. Your initial value times 1.05. And the reason we do 1.05 and not 0.05 is because we have to first multiply it by its initial value, which would be 40,000 times 1, and then we add on 0.05. So by multiplying it by 1.05, it keeps their initial value and then it keeps adding it on, adding it on. So that might be what this would look like. I would take my initial value and multiply by 1.02 times the number of years. It doesn't ask you to do that, but just so you understand, a common ratio or a percentage would be an exponential function. Okay. State whether the equation represents exponential, linear, or neither. We'll look at that. I can tell right away it's linear. And the reason I can tell is it's in this form. Y equals to mx plus b. This is the equation of the line. Y equals to something times x plus b. And this is your slope, which ends up being your common difference. All right. Okay, number 12 asks us to find the balance in an account with $3,500 principal, earning 3.6 compounded annually after 2 years. First of all, it helps to know that compound principal interest formula. I think in your book it's on page 311, and this is the formula. It looks something like this. The amount you're going to have will equal to the principal times 1 plus your rate divided by the number of times you're going to compound it per year, times that number of times you're going to compound it, times the time. And that's what the formula looks like for compound interest. So let's go ahead and plug in our amount. So our amount is going to equal to our principal, which is, we start with $3,500, and then we're going to add on, multiply by 1 plus our rate as a decimal. So 3.6%, we need to change that to a decimal, move it over 2 places, will be 0.036. Divided by the number of times we're going to compound it per year annually. So only 1 time per year, okay? And then we take that to the number of times we compound it per year once. And then the number of years, time, which is 2 years. So simplifying this, it looks like this. A equals 3,500 times 1 plus, well, let's actually even simplify the 1 plus. Let's go. 0.036 divided by 1 is just 0.036. 1 plus 0.036 is 1.036. And then 1 times 2 is 2. So simplifying this, look what I have. I have an exponential function. Y equals the initial value times my base raised to a power. Y equals a times x to the b. Okay. Just like before, we do 1.36 because I'm increasing by a percentage. I do it times 1 because that multiplies this by itself and it keeps the 3,500. And then it adds on the 36% every time I do this to a power, just like we did with the books. Okay, so this is an exponential. And when I multiply it by 1 plus the percentage, it keeps tacking on that amount to the 3,500. All right. So once again, I have my exponential function. It looks like this. And all I do is simplify it. I just plug in 1.036 on my calculator, square it, and multiply it by 3,500. And there I have my answer. When I do that, I'm going to get 3,756, so $3,756, 0.536, round that up to 0.54. And there you have it. So you're going to have $3,756.54 after you compound at 3% interest after 2 years. Okay, tell whether the equation represents exponential growth or decay or neither. Looking at this, it's pretty simple. Y equals your base, A times your base, that's my base, to a power. If this base is bigger than 1, it cannot be equal to 1, because if it's equal to 1, 1 to the first power is 1, 1 squared is 1, 1 cubed is 1, 1 to the... If your base is 1, you don't have an exponential function, you just have a line. So your base cannot be 1, all right? But if your base is bigger than 1, you have an exponential growth, okay? If this base is bigger than 1. Because if it's bigger than 1, if I have like 1.5 or 1.6 or 2 or 4 or whatever, and I keep taking this to a power, it's going to increase exponentially. Okay? If this base is greater than 0, but less than 1, so basically if your base is a fraction between 0 and 1, what you're going to have is decay. Okay. If you look at that on Desmos, look at this. Okay, just to emphasize this, if you just look at a base, y equals to, let's type in, y equals to, let's just do 2 to the x power. Okay, and then if I go ahead and do y equals, if that base, so that base is greater than 1, if that base is between 0 and 1, if I do y equals, let's say 1/2, let's put that in parentheses, 1/2 to the x power. Okay, you can see now it's decay. So the blue line here is decay, and the red line here is growth. And that's because if I do my xy, if I just chart, if you'll remember in the lesson, if I just plug in points for x and y, for here, if I plug in 0, anything to the 0 power gives me 1. If I plug in 1, 2 to the first is 2. If I plug in 2, 2 squared is 4. So this is going to get big really fast. But if I plug in negative powers, 2 to the negative first is, remember, 1/2. So the negative powers become fractions and they get smaller and smaller and smaller. But if this is a fraction, everything gets flipped. If the base is a fraction, if I plug in 0, anything to the 0 power is once again 1. And that's what I get here. But if I plug in to the first power, well, 1/2 to the first power is 1/2. If I plug it to the second power, 1/2 squared is 1/4. So it's getting smaller and smaller, and I'm not able to write anymore. 1/4. Okay. And my pen is. Anyways, so I get smaller and smaller and going this way. Now look, if I plug in with my fraction with my base of 1/2, if I plug in a negative power, well, look what happens. 1/2 to the negative 1 is equal to 1/1/2 to the first power. And I flip the fraction, keep the top, flip the bottom, and that's going to give me out 2. So when I plug in a negative power, I actually get out a bigger number. If I take this to the negative 2 power, try it. 1/2 to the negative 2 power is 1/1/2 squared. Well, 1/2 squared is 1/4. And then I have to flip the fraction and I get out 4. So the negative powers actually make it bigger. So that's why the blue, as I get positive, I get smaller. And if I go to the negative powers, I start getting bigger. The negative powers give me a bigger fraction. So that's why when your base is a fraction, you get decay. You start out big, you get small. When your base is larger than 1, you start out small and you get big. Now your base can't be a negative number because then it's not exponential. Because when you take a negative number and you square it, you get a positive number. And when you take a negative number and you cube it, you get a negative number. So back to number 13, growth or decay, just look at your base. That's all you have to do. Because it's a fraction between 0 and 1, you have decay. Right? If that was bigger than 1, you'd have growth. Okay, this big ugly problem looks scary than it is. Again, super easy. A business purchases a computer or system for $2,000. The tax code allows them to take a portion of that purchase every year the computer system is used, so you get tax write-offs. If the value of the system is depreciated at a rate of 15% per year, the function that models the current value system is this. How much is a computer worth after 4 years? Now look at this function. Your basic equation, all you have to do here is plug in 4 years for time, and that's all you have to do to figure it out. But I just want to make you realize this. This is just a basic exponential. Your base here is a fraction between 0 and 1, okay? And the reason this is 0.85 at 15% a year, because it's depreciating. So you would have a whole 100%, and when you subtract off 15% per year, that's 85%. So that's why you have this formula, okay? The base is between 0 and 1, so it's depreciation, it's decay. So all you do is take f of x, and that's equal to 2,000 times 0.85, and then the time is 4. So you just plug this in on a calculator, bam, you're done. All right, so if I plug that in on a calculator, this to the 4th power times 2,000, I'm going to get 1044.0125, so we're going to go 0.01. That's about how much money you'll have, how much it's worth after 4 years. So this one was back like number 9. We're going to solve each equation. When you have exponents here and you're not quite working with logarithms yet, how you want to solve exponential equations is, you know this. If a to the x is equal to a to the y, okay, your bases are the same, then x equals to y. And it's true the other way. If x equals to y, then a to the x equals a to the y. Okay, that's an a and it's ugly, but sorry about that. So we're just going to use that rule. If we can get these to be the same base, then their exponents will be equal to each other, and I can solve for x up here in the exponent. So if this is a base of 4, and it's to the x minus 1 power, okay, I know I can get 16 to be a base of 4, because 16 is actually 4 squared, or 4 times 4. So I'm going to write 16 as a base of 4, 4 squared. Now they have the same base, so their exponents I can set equal to each other. So now I can say, well, x minus 1 equals 2. Solve for x. Add 1 to both sides, and x is going to equal to 3. So here I have my solution, x equals to 3. On to the next one. Okay, this one looks a little trickier because I've got a fraction here, but as long as I can write this as a base of 2, remember when things are in the denominator, I can write them as a base of 2 and give it negative exponents, right? That's how I get it off the denominator. So the same rule, if a to the x equals a to the y, then you know x equals to y. And a lot of times the book goes b to the x equals b to the y. It doesn't matter what you call that base, but can I get this to be a base of 2? Well, 64, I believe, is 2 to the, what, 4th, 5th, 6th power? Yeah, it's 2 to the 6th power. 64 equals 2 to the 6th power. I can write this as a base of 2. So I'm going to write this as 1 over 2 to the 6th power. Now that doesn't help me. What I have now is 2 to the 3x equals 1 over 2 to the 6th. I don't have this same base. I need this just to be 2 to the 6th, not 1 over 2 to the 6th. Well, I can use the rule of the reciprocals. When I have a negative exponent, I write it as 1 over this. So undo it. take it to the numerator and write it as 2 to the negative 6 power. Well, 2 to the negative 6 power is equal to 1 over 2 to the 6. When you do that, now you have a base of 2 on the numerator and write it as 2 to the 3x equals 2 to the negative 6. Now you have the same base. The exponents are equal. 3x will equal negative 6. Solve for x, divide by 3 on both sides. X is going to equal negative 6 divided by 3 is 2. So x equals 2 is the answer to number 16. Oh, I'm sorry. Negative 6 divided by 3 is negative 2. Shame on me. Shame, shame. I almost forgot my negative. All right, find the common ratio for the geometric sequence 15, 150, 1500. I can see here it's going to be a multiplier of 10, but to figure out the common ratio, how do we get from here to here? How do we get from here to here? You're going to take your second term and divide it by the first term, because the opposite of a multiplier would be divide. So you would just go 150 and divide by 15. Well, 150 divided by 15 is 10. You can check term 3 divided by term 2 and make sure that is also 10. And this will cancel and you'll end up with 150 over 15, which is also 10. And you can do it for this and this and you'll end up with 10. So the multiplier would be 10. And that would be your common ratio. All right, on to, okay, the recursive formula, different than the explicit. Okay, so let's look at the recursive formula. The recursive formula is different than the explicit formula. The recursive formula just tells us how to find the sequence. So first you have to tell me what the first term is. So I have to know where to start. Then you're going to tell me to find any term after that. You're going to take the previous term. So this is any term. You take one before it and multiply it by the common ratio. Okay. The explicit formula looks more like an exponential function, and that the explicit formula is to find any term. You would start with your first term, A1, that would be your first term, and then your base is your common ratio, and then you take that to 1 before its power. So if you want the fifth term, you would start with the first term, multiply it by your common ratio, and take it to the fourth power, because you're going to do it 4 times to get to the fifth term. We are not looking at that. We're actually looking at the recursive. This is explicit. We want the recursive formula. It's just this. So all I do is I start with my first term and I say, okay, well, my first term is 5. Okay. And then I say any term is going to be 1 less times my common ratio. Well, I got to find that. My common ratio, to get from here to here, I multiply by 2. To get from here to here, I multiply by 2. To get from here to here, I multiply by 2. Or I take my second term and divide it by the first term and do it. So I go 10 divided by 5, which is 2. Okay, so my common ratio is 2. So here is my recursive formula. You start with your first term and to find any term. Let's say I want the third term. The third term would mean I would take 1 before it, the second term, 3 minus 1, which would be the second term, 10, and multiply it by 2. So the third term, a sub 3, would be 10 times 2. Well, a3, or the third term, is 20. It is. The third term is 20. Okay, and that's all it is. Okay, number 19 we're going to look at combining functions. This one asks us to do f minus g of x, and then after we do that, we plug in 4 for x. So recall, f minus g of x, that's just f of x minus g of x. Okay, f minus g of x just equals this. So I take f of x, which is 4x plus 5, and I subtract off g of x, which is 3x plus 1. And I'm going to subtract off that whole quantity. So I need to distribute this negative. So this would be 4x plus 5 minus 3x, distribute the negative minus 1. So if I simplify this, I'm going to get f minus g of x is equal to 4x minus 3x will just be 1x. And then 5 minus 1 is 4. So it's going to be equal to x plus 4. Now I need to find f minus g of 4. Well, all I have to do is plug in a 4 wherever there's an x. I plug in a 4 for x. So I'm going to go, well, that's 4 plus 4, which is equal to 8. And you're finished. Simple enough. Let's look at 20. If we have f of x is equal to this and g of x is this, I want f divided by g of x and then f divided by g of 1. So I'll plug in 1 for x after I've done it. F divided by g of x is simply f of x over g of x. So I'm going to take my f of x function, which is 3x minus 1, and divide it by my g of x function, which is 2x. Now, if this could divide or simplify, you would. You can break this apart, but it doesn't help you. So this will be f divided by g of x. Now we're going to do f over g of 1. Okay, so that means I plug in 1 wherever there's an x. So this would be 3 times 1 minus 1 over 2 times 1. Simplify this. 3 times 1 is 3. 3 minus 1 is 2. 2 times 1 is 2. 2 over 2 is 2. And simplify that, it's just 1. So f over g of 1 is equal to 1. And you're finished. Okay, when I'm working with square roots, one thing I like to do is I like to remember my biggest perfect squares. Instead of breaking into primes, which works fine, and then finding doubles so you can square root them, I like to think, what's the biggest perfect square that divides into this? Sometimes I'll just come up here and write my perfect squares. Like 1 squared is 1, and then I go 2 squared is 4. 3 squared is 9. 4 squared 16, 5 squared 25, and so on. So I'm just going to write all of my perfect squares here just so I can refer to them and think, what's the biggest perfect square that will divide into these terms? Because if I have a perfect square, I can square root it and pull it out of the radical. So all of these are perfect squares, and when I square root them, I get a whole number. So let's go ahead and look. Do any of these perfect squares divide evenly into 128? Well, play with it. I'm thinking 64 is going to work pretty good. 64 is actually 64 times 2 is 128. I said that wrong. 64 times 2 is 128. So I could have broken this into primes and gone 8 times 8 and 2 times 2 times 2 and pulled those all out. Or I could just go, well, that's the biggest perfect square that divides evenly into this. And that's how I like to do that. So now what I have is negative 5 times the square root of 64 times 2. This is the perfect square. 64 is 8 squared. So I'm going to take the square root of it and pull it out of the root, and I'm going to put it as 8 times, not 8 minus 5, 8 times negative 5. And now it's no longer in the root. So what I have now is 8 times negative 5 times the square root of 2. We'll simplify this. 8 times negative 5 is negative 40 times the square root of 2. And you're done. All right, on to 22. Whenever you have two radicals, you can multiply them together and put them under the same radical. Sometimes it helps us simplify, sometimes it doesn't. This is going to be 18 times 75. Let's see what I have here. 18, I know the biggest perfect square that divides into that would be 9. So this would be 9 times 2. I could pull that out. 75, the biggest perfect square that would divide into that would be 25. It's 25 times 3. Well, I have a 2 on the outside, so what I'm going to do is, here's my radicals. The square root of 9 can pull out and become 3. So 3 times 2 on the outside. The square root of 25 can pull out and become 5. So 5 on the outside. So that's no longer in there. And I have 2 times 3 on the inside. That's 6. Neither of these are perfect squares and they don't help me out. So I'm going to simplify this. 3 times 2 is 6. 6 times 5 is 30. So out here I have 30. And under the root I have 2 times 3, which is 6. 30 root 6. And that would be that most simplified. All right, let's come down to 23. This one's a little bit longer. It's a doozy. Okay, looking at this one, we've got 8 on the outside and we've got all this stuff on the inside. So I'm just going to go ahead and simplify it. Let's multiply the radicals together and multiply the constants together. Remember with multiplication, you can go ahead and switch around the order. 2 times negative 8 times, let's say, x, is the same thing as negative 8 times 2 times x. It doesn't matter what order I multiply these in, you're going to come up with the same answer. Multiplication is commutative. So I can go ahead and write this as negative 8 times 4. And then the radicals, I can multiply and put it all under one radical. We'll have 15 times h times k squared times 5 times h times k. All right. And on the outside, 8 times 4, let's just simplify that a bit. 8 times 4 is negative 32. So that's what I have. And on the inside, let's simplify this again. We have 15 times 5. Well, instead of multiplying that out, I'm going to break this up. 15 is 5 times 3. And we have another 5 here, times 5. And then I have an h and an h, so I do have an h squared. That's good. And I have a k squared and a k. I'm going to leave this, instead of writing k cubed, I'm actually going to leave it as k squared times k, because I cannot pull out a k cubed out of the root, but I can pull out a k squared. So with constants, or excuse me, with variables, you want them to be in even exponents so that you can pull them out of the root. So let's see what I have here. 5 times 3 times 5. Well, the 5s can be written as 5 squared. So I'm going to go ahead and pull the 5s out and put them out here. So 5 times 5 is 5 squared, and the square root of 5 squared is just 5. So here I'm left with 3. Now let's go ahead and look at our variables. I have an h squared. Well, I can square root h squared and just bring it out here and make it h. That eliminates that. K squared, I can pull this out and make it just a k. That eliminates that. And I'm left with 1k on the inside. So let's go ahead and see what I have. I have kh 5 times, this is not a minus, this is a times negative 32. Well, 5 times negative 32, I'm going to write it over here, is negative 160. And I have a k and an h. I'm going to write h first, then k, just because it's in order alphabetically. Then I'm going to multiply that times the root. What's left inside is a 3 and a k. And there you have it. That's this fully simplified. Now remember, with constants, you're looking for a square. When you have variables, if I have k cubed, anytime I have something that is odd, I break it down into a square and one left over, because the square will pull out. That would work if I had k to the 5th. Okay, I would break this into k to the 4th times k. So an even and an odd. Because if I square root k to the 4th, I pull this out and I get k squared, and it leaves me with k on the inside. So anytime you have an odd number for the exponent, break it into its even with one left over. That's why I didn't put this as k cubed, because it doesn't help me to square root the cube. I want it k squared with one left over. Okay, guys, just a little explanation there. Okay, guys, this one's going to be a little bit of work here. Let's go ahead and simplify under the radical first. X divides into x squared and leaves you with an x on the bottom. So what I'm going to have is the square root of 5 over 49x. Now 5 is not a perfect square, but 49 is. So go ahead and break this apart. You can break this into the square root of 5 over the square root of 49x. Okay. They're both under the radical. When you divide them together, they're under one radical, or you can separate them. Well, the square root of 49 can be pulled out, and it's just 7. So now I have the square root of 5 over 7, and the x is still under the radical, square root of x. Now that looks most simplified. I can't pull the 5 out. 7 and 5 don't divide out, square root of x. However, remember, you cannot have radicals on the denominator. You have to rationalize, okay? Rationalize. You need to multiply top and bottom by the square root of x to get rid of that radical on the denominator. So if I multiply this by the square root of x, I'm left with square root of 5x, and on the denominator I'm left with 7. Square root of x times square root of x is square root of x squared. Square root of x squared. And the square and the square root cancel, and you're left with x. And that will be your solution. So don't forget to rationalize your denominator. All right, when you're looking at this function, if you look at just the graph of, f of x equals the square root of x. That's going to be this graph. And then since I'm inside the radical, anytime you're inside, this shifts you left and right and it's opposite because the function looks like this. Y equals to some value times x minus h, and then the plus k is on the outside. So this is a minus, so it's the opposite. If it's minus 5, I actually shift. This shifts to the right 5. And the outside is your up and down, and it's straightforward. It's not the opposite. So this shifts this graph to the right 5. So if I know what this graph is, I can just move it to the right 5, or I can come over and just do this. If you want to do an XY chart for this, start with 0. The square root of 0, that's just 0. Then plug in 1. The square root of 1 is 1. I'm not going to plug in 2 because the square root of 2 is not a whole number. I'm going to pick a number that I can get a perfect square. I'm going to pick 4 next. The square root of 4 is 2. My next perfect square would be 9, and you can pick that. Put in 9. The square root of 9 is 3. Try negatives. -1. Does that work? What's the square root of a negative number? What number, when I square it, gives me -1? Well, when I square anything, I get a positive. So that doesn't exist. There is no number. So this is undefined. Okay? It doesn't exist. You cannot square root a negative. So I have to stop at 0. Now that would be what this graph looks like. I'm going to shift it to the right 5. So what I'm going to do is when I plug in my x value, I subtract off 5. So now look at this graph. All right. So if I were to just graph the original graph, here's 0, here's 1, 1, here's over 1, 2, 3, 4, and up 1, 2, and here's over 4, 5, 6, 7, 8, 9, and up 3. So my original graph looks like this. Okay. Inside shifts left and right. Outside shifts up and down. We have an inside. Okay. So basically what this tells me is I shift to the right 5. So I'm going to take this graph and shift to the right 5. 1, 2, 3, 4, 5. Take this point, shift it to the right 5. 1, 2, 3, 4, 5. Take this point, shift to the right 5. 1, 2, 3, 4, 5, and so on. So your whole graph shifts to the right 5, and it looks like this. Check it. Just plug in points. Plug in 0. If I plug in 0, 0 minus 5 is the square root of -5. It doesn't exist. That's why I don't have a point here at 0. I can't do 1, 2, 3. The first point I can do is 5, because if I plug in 5, 5 minus 5 gives me 0, and I finally get a point. If I plug in 6, 6 minus 5 gives me 1, and the square root of 1 is 1. So I have my point 5, 0, and my point 6, 1, and so on. And you can plug in points. Or you can just do this regular graph and shift it to the right 5. We did the regular graph, and we shift every point to the right 5. All right, guys, that's how you do this benchmark, or this practice benchmark, sorry. Good luck, and email me. Let me know if you have any questions, and have a great day.